So let's now illustrate the principal component analysis. First, we will look at what we call the proportion of variance. You know, each eigenvalue lambda I indicates somehow the contribution of the component associated to the variance. So we can get what we call the proportion of variance, which is explained by the k principal component. So if we just sum the lambda for the k eigenvectors, k components that we keep, and we divide this by the sum of all eigenvalues from 1 to d, we will get some proportion of the variance that is captured by our k principal components. And so that's quite useful if we want to keep 90% of the variance of the information. We need to look at this that way. We need to make the summations and figure out whether or not we are in the right place at the right configuration. So if we have an high correlation between variables, if all variables are quite correlated, with only few components, we should be able to capture most of the variance. So very few of them will have high values. And with these, we should be able to represent many things. So this is one case. In the other case, if they are not that much correlated, if they are independent, and if they are contributing somehow, varying somehow in a relatively good way, we could expect to have many eigenvalues with not null values, but some kind of similar values over the range of all eigenvalues. We can use what we call a Scree plot. This is for plotting in decreasing order, in decreasing eigenvalues order, the information we have, what's the proportion of variance. So the Scree plot, for example, for MNIST, if we apply PCA to MNIST, we can see that with the first, I don't know, 50, say the first 50 eigenvalues, we are capturing many things. We are capturing many values. So we can see that we have about 60% of the variance captured with about 50 components eigenvectors. If we go to 300, it's kind of close to 95, I would say. And we see that the values here are relatively small. And from 300 to nearly 800, 700 and something, we see that the contribution is quite low. So basically, we can see that in that first part here, basically that part here, this is where we are getting most of the variance, most of the useful information for our problem. So here's an example of PCA in 2D. So basically we are mapping MNIST, which is in 700 and something features dimensions at first, with the grayscale pixels. We are mapping this into two dimensions. So this is a drastic compression, but that's really good for visualization. And now we just superpose the real images in there. So we see that there is some relation, you know, all the 7 and 9 here are looking quite similar. And we have things like zeros here with some 5 and 6, which are also quite similar, with even an 8. And we have the ones here that are there. So basically kind of capture some distribution of the data over that space in 2D. We can also look with, still again with MNIST, at the reconstruction of the characters. You know, if we have this original 7, if we use only one eigenvector, we have that thing, which look like some average 9 or 8. It's unclear. It's probably not enough. But if we go with more and more components, it says at 2 it's not enough, but at 20, we are recognizing a 7. Even though there is some gray around it, so it's not perfect, we are capturing most of the 7 at 20, and at 200, it's kind of quite good. We have some artifacts around the characters in terms of the light grays, but the 7 by itself is quite well drawn. Similarly, for the 9 here, we see that at first it was struggling. So we see that at 20 here, it seems not that much working. We see some kind of 9, but it's far from being perfect. With 200, it's much better. Of course, we still have the gray values in the background, but the black ones are quite good. some other examples with 1. So with a 1 here, we see at first that it's always start with some kind of 9, 8, something like this. So at first it is not that good, but over time it's getting well. And you know, with 200 is kind of really great. 7 also is really great at 200. So PCA basically explains the variance of a data set. So we are able to explain it in some ways. So it's good for that, but at the same time, it is sensitive to outliers. So if we have an outlier that is bringing up a huge variance, it may influence a lot the performance. It may not be the right thing. So this is to be taken really cautiously. It's very interesting for visualizing data. So it's a very useful tool to plot complex high dimensionality data in like 2D, 3D. The point is that for high dimensionality also, when the D is large, a computation of S can be quite heavy, it's D square, but there are some advanced methods that are more robust to that. We can lower this to something like K times D. So we can be linear according to D versus quadratic, which is really, really expensive in that case here, while here it's much more manageable, especially if K is small. We are losing, in fact, completely the significance of the variables. You know, if we are dealing with measurements in millimeters, well, here after the PCA, we are losing all of this. There's no physical units in there. It's kind of mixing up things together. So if we have different variables that are not related at all, they may be mixed in the computation of the components. And so this is not useful for that. This can be an issue depending on what we are doing. One way to look at it is also the idea of reconstructing somehow the elements. So we have what we call the data reconstruction, which is a projection in space of Z. So basically we say that we have ZT, which is equivalent to the PCA coming from W transpose minus the average value here. So this is our projection in space Z. Since W is orthogonal, we know that W times W transpose is equal to identity matrix. So we can say that, okay, let's W times Z T is equal to W transpose times X minus mu, the average value. So simplifying things here, you know, this thing should be, it is equivalent to that. So we are kind of building up, mapping back the Z from Z to X. We have what we call X at, which is corresponding basically to, we'll just start back on that. We have this X here. If we just take the mu and we move it there, and we know that this thing is in the identity, we don't need that. We are able to say, okay, down that X transpose at is equivalent to WZT plus mu. Because this thing is going there. Yeah. So PCA is minimizing the reconstruction error. Basically, we can look at this by saying, okay, what is the difference between the reconstructed X and the original X after passing through the PCA? And usually the criterion is made so that we will minimize this error, reconstruction error, by doing this. And so it depends directly on the number of components KU. So if we have a bad reconstruction error, it means that we don't have enough components K. So if we look at what we call eigendigits, this is an interesting element. It's a way just to extract somehow, like from the MNIST. I don't remember if it was with MNIST, but it's likely to extract the different eigenvectors that are coming from the covariance matrix. And we can see here different things, you know, at the first, I see here a 0, while at the second eigenvector, I see things that, well, it's complex, you know, there is a 3 here like that, but there is some kind of white background that may mean something else. Here we have something else that may look as a 9, but there is something that I don't know, but maybe closer to a 6. And like this thing, we have a 3 here. So we can see that we have some phantoms of, I would say, characters here with the first eigenvectors. While in the last ones, the one at 300, 400, 500, 600, the information is not useful. It's basically looks like salt and pepper noise. We don't know much what it gives, but it seems to be giving a little more in terms of the quality of the results, but I'm not sure that it contains any useful information in there.